I want you to take a moment and pause and think of a star. Some of you may think of those little twinkly things above our heads, but some of you may think of someone from Hollywood. Although you may think that these movie stars are a big deal, in the grand scheme of life, they're nothing compared to the real stars outside in our cosmos. And compared to Hollywood stars, the birth of a real interstellar star is much more interesting. Stars form in cold molecular clouds of dust and hydrogen gas. These gas clouds can float out in space for millions of years undisturbed, but once something comes along to disturb this gas cloud, all the action begins inside of it. This disturbance kicks off the gravitational collapse of the gas cloud, and the cloud can begin to fragment into multiple blobs, paving the way for a binary star or a star cluster. In these collapsing blobs, the rise of pressure and density causes the temperature to rise and a protostar is formed. They will become real stars when they begin to fuse hydrogen in their cores. This formed protostar begins the process called accretion. It adds layers and layers to itself. As this protostar is forming, outflows begin to occur from the disk. Once the accretion is finished and the outflows have ceased, there's still some material left over around the protostar. This leftover stuff may develop into planets or dwarf planets. Once finished, all that is left of the once large cloud is a star that is orbited by the planets that are around it and a disk of leftover material. For a star to transition from protostar to star, it first must add layers to itself and grow, eventually reaching equilibrium. Equilibrium is when the pressure of a star pushing outwards equals the force of gravity pulling inward. Think of this as two teams playing tug of war. If they're evenly balanced, they'll never move. Once this star reaches this point of equilibrium, a solar mass star's core has reached a temperature of 15 million Kelvin when it begins to fuse hydrogen into helium. In very simple terms, it takes some hydrogen atoms and furiously slams them together to produce helium. This fusion of hydrogen produces a large amount of energy, which in turn produces the light that the sun shines to Earth and the rest of our solar system. Stars can burn hydrogen for a very long time, but this fuel is not infinite. Eventually, it will move on from fusing hydrogen, and depending on its size, it can begin to fuse the heavier elements. Eventually, however, the temperature of this red giant surface will be much lower than when it was fusing hydrogen in its core. Thus, it has a reddish color. With the core no longer producing energy, the star's gravity overtakes the outward force, and the star's core begins to shrink. As it shrinks, the pressure inside the core of the star increases, thusly increasing the temperature. Eventually, the core of the star reaches somewhere close to 100 million Kelvin, and the helium in the core begins to fuse. At this point, helium can begin to fuse gradually, or it can start with a violent explosive flash. As helium begins to fuse, carbon and oxygen are produced in the core. For stars bigger than the Sun, the core can keep the fusion cycle going, making all the elements we find in the periodic table until it reaches iron when fusion ceases. The life of a star is an interesting and complex sequence of events. However, it can be simplified using the Hertzsprung-Russell diagram, or the HR diagram. This diagram plots the temperature against size, showing the relationship that temperature and luminosity have. The hotter a star, the brighter it is. The bulk of stars fall along the main sequence. That's the concentration of stars that form along a diagonal line in the diagram. From the main sequence, a star moves off onto a different branch of the HR diagram, first to giant, then to white dwarf. On the HR diagram, stars fall into one of the spectral sequences, and it's labeled by its brightness. These labels are O, B, A, F, G, K, and M. Type O stars are the brightest on the temperature range, and M is the lowest. For example, our Sun is classified as a type G. The HR diagram may show the life of a star on a graph, but what actually happens is much cooler. Metaphorically so. It's actually extremely hot. A red giant star, as it ages, starts to shed the ionized gas that's located in its outer layers. This expanding shell of gas is called a planetary nebula. Nebulae come in many shapes and sizes. The Ring Nebula can be found in the constellation of Lyra, It spans 1,000 light years across and is visible through a small telescope. Another nebula that is easy to locate is in the constellation of Gemini, called the Eskimo Nebula. These nebulae that are remnants of stars harbor a hot core in the center that will eventually cool to become a white dwarf. At the end of the life of a normal star, a white dwarf is formed. White dwarfs are extremely dense stars and are made of carbon and oxygen. Imagine the entire sun being packed into a space the size of the Earth. Such a small size makes white dwarfs very dim, although they have a high temperature. The brightest star, Sirius, has a dim white dwarf companion. Sometimes a white dwarf can have a companion star. If the companion becomes a giant, it could spill matter into the dwarf's area of gravitation, passing what's known as the Roche lobe. As the white dwarf's mass increases due to this excess spillover, it can only remain unresponsive until its mass has reached 1.4 times the mass of the Sun, known as the Chandrasekhar limit. If the star exceeds this mass, it will become unstable and explode into a Type 1 supernova. The path a star takes at the end of its life depends on its size. Dealing with smaller stars, a Type 1 supernova happens. These Type 1 supernova occur when a large amount of matter has been dumped on a white dwarf. This has made the white dwarf unstable, which will cause it to explode. Iron is the stopping point because of the small amount of energy that is produced by iron fusion not being enough to hold off the inward force of gravity. Without enough energy being produced by fusion to hold off gravity, it's able to take over and the large mass star contracts rapidly, eventually imploding into a supernova. The power that is produced by the supernova explosion moves throughout the fabric of space-time, affecting change throughout the universe. The ripples created by a supernova can be enough to set a cloud of dust into motion and produce more stars and planets. These ripples also help to spread out the elements that were produced by the star when it fused them. The after effects of supernova explosions can be wide-ranging. Some can leave behind cooling neutron stars, like the Crab Nebula, while others leave behind black holes. Neutron stars are the remnants of cooling stars, forming from the remains of stars that are close to 3 times the mass of our Sun, but are comprised mainly of neutrons. These neutrons are the particles remaining from the atoms that were fused during the star's lifetime, and they are densely packed into an area roughly the size of Manhattan. This would be comparable to the Sun being compressed into an area about 12 miles across. To understand the density of a neutron star, a single teaspoon of a neutron star would outweigh Mount Everest. This incredible density means that the neutron star has a powerful gravitational force. Due to the gravitational force, neutron stars rotate faster than most planets and develop a strong magnetic field. Some neutron stars can form pulsars, meaning that they radiate electromagnetic waves of light in cone shapes, kind of like a lighthouse does. As charged particles spiral along the neutron star's strong magnetic field, they emit radio waves in the polar regions of the stars. Because they only fire radio waves in a cone, they can only be detected by radio telescopes when the cone is facing the planet Earth. The rapid spin of the pulsar makes these flashes turn on and off within microseconds of each other. Neutron stars do, however, have a set amount of energy, and over time they begin to cool, slowing their rotation. Black holes are one of the endpoints of a star's life. These black holes are remnants of a high-mass star that went supernova. These black holes have 2 main categories, stellar and galactic. Stellar black holes are formed on the life sequence of a star, whereas the origins of galactic black holes are unknown. Galactic black holes are proposed to sit at the center of every large galaxy. If the Sun were to become a black hole, it would pack its entire mass into an area as small as Slippery Rock. Black holes are characterized mainly by the indomitable gravitational force that they produce. This prevents any form of electromagnetic radiation from escaping from inside its event horizon. Because of how little we know about black holes, the laws surrounding them are very fuzzy, and even discovering them is done by observing stars orbiting around the black hole itself. From the orbiting star's motion, one can deduce the mass of the undetectable object. If this mass happens to be larger than 3 times the mass of the Sun, this object would probably be a stellar black hole. Recently, LIGO detected gravitational waves from 2 colliding black holes. This has opened a new and exciting area of research, and the future of discovering black holes looks very promising.